Today we will look at a remarkable simple idea that when we move, time runs more slowly. So is time the same for everyone? Well, as you might guess from the title of this video, the answer is no, especially if you're an astronaut traveling at high speed. And this was a discovery made by Einstein. Let's look at a light clock. A light clock consists of two mirrors between which photons are bouncing, and we can consider one tick to be when the photon makes a full traversal from bottom to top and then back down again. Now, let's imagine that we're sitting on a train and we are performing this experiment where we're watching a photon bounce up and down. Now, for us, this motion is obviously vertical. The photon goes up vertically and comes back down vertically. But now let's imagine that we are standing on a platform watching the train go past. What will happen to the path of this photon? Well, it will now be diagonal. So it goes from being a vertical path from the point of view of when we're sitting inside the train to a diagonal path. But light has the same speed regardless of whether we're sitting inside the train or standing on the platform. So let's see what the consequences of this are using simple geometry. Suppose the train is traveling at a speed or velocity v. From the platform, the train has traveled a distance v times delta t prime in a time delta t prime. And that's the time it took for the photon to go from the bottom mirror to the top mirror. Now, how far has the photon traveled from our point of view? Well, it's traveled a distance of c times delta t prime. But sitting in the train, the photon went vertically upwards, and so it traveled a distance of c times delta t. Now, using nothing more than Pythagoras' theorem, we can write down this relationship here, that the hypotenuse squared is the adjacent squared plus the opposite squared. And so what do we get? Well, we get this second equation here, from which we can write delta t prime squared times some factor is delta t squared. So what is delta t prime from this relationship? It's equal to delta t divided by this factor, the square root of 1 minus the velocity of the train squared divided by the speed of light squared. So let's call this factor gamma, 1 over that square root, 1 minus v squared over c squared. How does this factor behave? Well, v, the velocity of the train, has to be less than the speed of light. And so v squared over c squared is less than 1. And therefore the square root at the bottom is going to be less than 1. And so gamma itself has to be greater than 1 because we're dividing 1 by a number that's less than 1. Now, as v tends towards c as it approaches the speed of light, as the train is moving faster and faster, that term will get bigger and bigger. We conclude, therefore, that delta t prime, the time for us as we're standing on the platform, is longer than the time for the same event for the photon to go from the bottom mirror to the top mirror than if we were to be sitting on the train. And that time gets longer and longer as we move faster and faster. So by the time we get to 0.99 c, almost at the speed of light, time is moving 7 times slower on the train. Now, this is not science fiction, this is a reality. In fact, GPS satellites have to correct for this relativistic effect, otherwise their positions would drift. Now, this is only the first part of the story. The second part of the story is length contraction. Things get shorter as we move at higher and higher speeds, and that's what will come next.